All right, so the goal for today is to talk about the property of matter known as electric charge. So a lot of this will likely be things we're familiar with, but again, we're putting it on more firm, physics footing, so that we can really talk meaningfully about what's going on here. So electric charge, you are familiar with, if you've ever kind of rubbed your feet on a carpet and then tried to touch someone, you might feel a jolt or a shock. Or you might have, rubbed your hair on a balloon and notice that your hair kind of goes crazy next to a balloon, or you can even sometimes rub a balloon on your hair and then have the balloon kind of hang on the wall. So there is this thing called electric charge, and it results in either attractive or repulsive forces acting on objects that possess this charge. And we can ask ourselves how we might have motivated historically, right, our understanding of charge, right? So just to give an example, I have some kind of paper I've ripped into pieces. I could take a balloon, I could rub my hair with the balloon, and then I notice that if I bring the balloon close to the paper, it flies to the balloon, some of it sticks to the balloon, and the rest is now just a mess on my table. So, something happened to that balloon. When I rubbed the balloon to my hair, something happened to the balloon, and I could do the experiment where I kind of touch the balloon to the ground or have it touch other objects and don't really do anything with it for a while. Then if I were to just hold the balloon up to the paper in that case, nothing really happens. When I rub my hair on the balloon, then something does happen. That act of rubbing did something to the balloon. So what's going on? In this case, we now know that charge, right, the balloon gained charge in this case. In this case, it gained a negative charge, right, which we learned through experiments. But people, without knowing what causes charge or what it is, right, something happened to that balloon. They gave it a property that we call charge. And we can do some experiments to show that there are clearly different flavors of charge. So I have a couple of YouTube videos I grabbed. So here's an example of a balloon, which is just kind of hanging. And then we bring near it a piece of plastic, a plastic pipe. And when they're both kind of, nothing's been done to either, they just kind of, nothing happens. They don't seem to be attracted or repulsed from one another. We're going to take the balloon and rub it against some fur. Do that for a little bit. And then we're going to take the rod and also rub it against some fur. All right, I think we get it. Da-da-da. We're going to take the pipe and rub it. It looks like we're rubbing it with silk in this case. And when we hold them near each other, something seems to happen. In this case, there does seem to be some sort of force between them. In this case, they seem to be repulsed. The balloon is trying to go away from the pipe. There's something's going on there. We can contrast this if we instead take a balloon, and again, and we're going to move a piece of glass near it. And originally, kind of nothing happens. They don't seem to be attracted or repulsed from one another. We rub the balloon again, and then we rub the glass again, or the glass this time. And this time, when we bring the glass near the balloon, now it seems like the balloon is attracted to the glass. So again, there seems to be some sort of force between them. They don't even have to be touching. In this case, it's attracted, they end up touching. But the balloon is moving even when they are not touching one another. Something is going on, and it's different than it was for the plastic. So that motivated or suggested the idea that there are two different flavors of charge. Let me just see if we can summarize this with a couple experiments, right? We have kind of a balloon which is rubbed with fur and kind of jumping to the answer. That did something to the balloon, which gave it a particular flavor of charge. I'll put some minus signs there. And then we took a piece of plastic and rubbed it. And it turns out when we rubbed it, it also got this kind of charge. So we have kind of balloon and pipe. And then we notice that in that case, they became attracted to one another. There was an attraction. Oh, sorry. They were repulsed by one another. Then we took the case of a balloon, and we rubbed it again with fur. So, by the reproducibility of science experience, we should expect the same thing should happen. You get some sort of flavor of charge. And then we took a piece of glass and rubbed it, and it got some sort of charge, such that when we brought these two objects close to one another, they attracted to one another. In this case, there was an attraction. And in the lab, you'll do further experiments where you'll take two pipes and put them near one another. So you have kind of one pipe and you rub it with some fur or silk, it gets some sort of charge. And then when you bring another pipe nearby that you've rubbed with fur, you should notice that they repulse one another. And then you'll take a piece of glass and you'll rub it with some fur or silk. And you'll take another piece of glass and rub it with some fur or silk. You should also notice that they repulse one another. And we should expect that whatever we did to one piece of glass, the same thing then happened when we did it to the other piece of glass. So whatever kind of flavor of charge they have, they are probably the same kind of charge. And then similarly for the two pipes. And then you should notice that when you take a pipe and rub it, and then bring near it a piece of glass that you've rubbed, that they should then attract one another. So see, this is kind of pipe, pipe, glass, glass, pipe, pipe. So then that motivates the idea, and then you can also think about magnitudes, which will be the next lecture when we try to quantify this. That if you rub the objects more and then bring them to the same distance to one another, they might be repulsed more strongly than if you kind of barely rub the two and then bring them to that same exact distance. So it also suggests that this force can be quantified, you can alter the magnitude, but this at least gives us a sense of kind of the directionality, and that there seems to be two different kinds of charge. So this all suggests that there is a property called electric charge. We'll say a property of an object called electric charge. And there are two different kinds, or two flavors of charge. And it was Benjamin Franklin, actually, that came up with the terms that we now still use. So, we call them, these flavors, positive and negative. Which are just names. They're nice in that positive and negative, we have mathematical associations with those, so that these bode well when we eventually want to quantify this. But he could have just as easily called them red and blue, Will and Grace, Taylor and Travis. They're just names that he came up with. But we now call it kind of positive charge and negative charge. And with it, we've already kind of seen that there are various properties that manifest themselves when you have these two flavors of charge. Like charges seem to repel one another, and opposite charges seem to attract one another, is one thing we've seen. But then physicists and scientists, continue to kind of study this idea of electric charge, and now we have a lot better understanding in terms of the properties that the properties that electric charge can have when a object has this particular property of charge. So let's just summarize them now. A lot of this you've already seen, but again, let's try to just kind of lump all the ideas together. So we now know of kind of properties of electric charge. We've just talked about one, that there are two kinds, which I'll just use the positive and the negative. Two kinds of electric charge, such that like charges repel and opposite charges attract. And that relates to what we will call the electrostatic force, which we'll start talking about in the next video. This is ultimately that charge is a property of an object. It is something that an object possesses. It is not an object in itself. Like, I cannot tell you to go up to lab and grab me a container of charge. There's not going to be anything labeled charge, in any of our cabinets. You can take an object and which can possess charge, as if, for example, when I rub, this is a balloon that is, it starts out neutral, has no charge on it. I'm gonna have to elaborate on what I mean by that. Really, what I should say is that there's no net charge on it when it is neutral. And then when I rub it with my hair, it then gains the property that it has a net negative charge. So it's a property of an object, not an object itself. Just to give you another example, like mass. An object has a property that we call mass. I cannot go up and find in a cabinet somewhere something that is mass. Objects themselves possess a property called mass. Just like how, say, and this is a little bit more subjective, but I could give a non-physics example, right? Different objects has a property that you might call softness, and different objects have a different amount of softness associated with it. If you want something, I can't ask you to go get me a container of softness, but I could ask you to bring me some object that has that property. You might bring me, a pillow or a stuffed teddy bear, compared to, nails or something. In our further studies of charge, we came to learn that charge is quantized. And by that is that it comes in discrete amounts. There is a fundamental unit of charge. And in order to have any sort of amount of charge, you have to have some sort of integer quantity of this unit. So there is the kind of fundamental, I think this is how your book defines it, charge. And typically it uses the symbol lowercase e for the fundamental charge, which quantifies the discrete packets of charge that you can find things in. And there can be positive versions of this, because we know that's one flavor, and there can be negative versions of this, because that's another flavor. But now if we're going to quantify this, we also have to come up with a unit that we're going to use to describe charge. And the unit that we use is called the coulomb. And its definition is actually based on currents. So we have not really done that yet for me to kind of properly define to you what a coulomb is. But let's just take it as a given, right? That there is this unit called a coulomb, and I can use that to quantify charge. And charge always comes in some sort of integer multiple of E, which is 1.602 times 10 to the negative 19 coulombs. So C, that is the coulomb, which is then going to be our unit of charge. And what is interesting is that, remember I've talked about that there are two flavors of charge, positive and negative. And so any sort of positive charge, right, if I have an object that has some sort of positive charge, that means there is some integer times E in terms of the positive charge on that object. But then you could ask, is it the case that for the other flavor, negative charge, is it still the same E, maybe with a negative sign, right? Every negative charge has negative E, negative 1.602 times 10 to the negative 19 coulombs, and some integer or whole number multiplied by that. And it turns out it is. But it didn't have to be that way. So this fundamental charge ends up being the same for positive charges and negative charges. So any object, at least in the context of this course, any object that has a positive or a negative charge will have some number multiplied by this fundamental charge amount E. And for negative charges, the convention is that we put a negative sign out front. And I'll say maybe a little bit more at the end of why it didn't have to be that way. You might think that's kind of obvious, you know, knowing kind of where charges originate from, but again, it didn't have to be that way. And for this course, it will always be quantized in terms of E. Actually, let's just write it down now. You know, we could ask ourselves then, what is the source of charge? Where do these two flavors of charge come from? You know, what actually gives an object a property that we can call charge? Well, as you likely know, these kinds of charges originate from atoms. You're all nice and familiar with atoms. I can just bring a picture over here rather than trying to draw it myself. If you were to Google around, right, this is kind of typical textbook, you know, example of an atom where there is this nucleus. The nucleus houses protons, which has a positive charge, neutrons, which are neutral. There's no charge on a neutron. And then around this nucleus is some sort of cloud of electrons where you can find the electrons roaming around. Typically, textbooks will draw it kind of like this, or at least kind of non-modern physics textbooks, where it kind of looks like the electrons are going around, like planets going around the sun. We now know this is not entirely accurate, but it's a good enough picture for us to understand that the sources of charge is that the electrons possess a negative charge. Each electron has negative E worth of charge, and then each proton has positive E worth of charge. So such that if you have an atom that has, say, 2 protons, so by the periodic table that would be some sort of helium atom. If that helium atom also has 2 electrons, then it has no net charge. We call that electrically neutral. If it loses one of those electrons, so it has 2 protons but only 1 electron, then it has more positive charge than negative charge. Overall, it has a net positive charge, in that case equal to 1 times this lowercase e. So let's summarize that real quick, and then maybe I'll do a quick problem with that. So atoms with electrons each having a charge of negative E, or negative 1.6, I round to just a decimal spot, times 10 to the negative 19 coulombs. and then protons with each having charge equal to plus E. So an object that has an uneven balance of electrons and protons is what gives it the property of having some sort of net charge, right? And I really should be saying net charge when I talk about this sort of stuff, right? So again, the example I gave of helium, 2 protons in the nucleus, that's what makes it helium. It also has 2 neutrons in the nucleus, or at least the standard isotope has 2 neutrons in the nucleus, but those don't have any charge. Then if it has 2 electrons kind of orbiting around the nucleus, it has a net charge of 0. If it's ionized, which means it might lose one of the electrons, then it has a positive charge. It could lose both electrons. Then it has a net charge that's 2 times E. Or you could have ions where maybe actually helium I don't think can do this, but you could have, let's use hydrogen for example. 1 proton in the nucleus, it's actually the entire nucleus. And so then if hydrogen has 1 electron orbiting around it, it has no net charge. If it loses the electron, it has a net positive charge. But then you can also have what's called an H- ion, where you can have a hydrogen atom with 2 electrons orbiting around it. So then it has a net negative charge in that case. The ion actually is very useful in terms of the radiation that comes off the surface of our sun. A lot of it comes from interactions with these negative H ions. So, and just as an aside, that's kind of just an aside. In this class, it will always be integer multiples of this fundamental constant E, the fundamental charge unit E. And to just give you a clue from modern physics of why this didn't have to be the case, is that the electron has a charge of negative E. And in the current particle physics model, the electron is a fundamental particle, which means you can't take an electron and cut it open and look inside. There's nothing, right? It is the smallest, is the smallest fundamental kind of particle, right, that manifests itself as the electron. Versus a proton, which has a charge of plus E, but you can cut a proton open and look inside. And there are these things called quarks. And different quarks possess charge, but they possess charge in like 1/3 or 2/3 multiples. So in the particle physics world, you can have things like quarks that have an overall charge of 2/3 times E, or 1/3 or negative 1/3 times E. But then it just so happens that the protons that make up normal matter have the right combination of quarks such that the overall charge in a proton is an integer multiple of this E, which is the exact same E as the electrons, though again, doesn't seem like that had to be the case, though it happens to be that it is. And we're glad that it is, because actually you can do these experiments where if you change, or these thought experiments, where you can change the kind of relative value of this E for protons and electrons. And it turns out the periodic table gets really unstable if you play around with that value even a little bit. So the fact that we're here and the fact that normal matter can do what it does really does rely very strongly on the fact that this E is the same for electrons, which have negative charge, negative E, than protons, which has the exact same amount of charge, but it's positive. So what this also says is that all normal matter has charge, right? All normal, unless you claim you're made of dark matter, which to our best understanding, it cannot possess charge. We all possess charge. I'm made up of protons. There's plenty of electrons that make me up. I have charge overall. Now, more often than not, things are more or less electrically neutral, which means that I possess the same amount of positive charge as negative charge, and so that overall I am neutral. But sometimes I feel like the jargon can get a little confusing, right? When you say something does not have charge, really what that means is there's a net charge of 0. Because again, I can't completely devoid myself of protons and electrons and hope to still hang around, at least in my current state. So in that case, we all possess charge, but then we can think about the net charge, which is an excess of positive charges versus negative charges. That's what we mean by that. So just to give a quick numerical example, suppose I'm told, right, so suppose I tell you an object has a, and I'll even put net to emphasize the point we're trying to make here, a net charge of, and typically Q is used. You'll see Q used a lot as the symbol that represents the charge of an object. Just how we always use lowercase m typically for like the mass of an object, right? Often Q is used to tell you about the charge of an object. Suppose I tell you that an object has a net charge of Q equal to, and I'll even put the plus to make it clear, plus 2.27484 times 10 to the negative 17 coulombs. And I could ask, how many fundamental charge units really what I mean is kind of in excess are on the object. So conceptually, we can start by asking ourselves, what does the fact that this is positive mean? You know, those are a multiple choice question on an exam. You know, does this mean that there's more positive charges than negative charges, more negative charges than positive charges, a dearth of negative charges versus positive charges, right? You can think of all these different combinations. And sometimes it's ambiguous, where there are multiple ways. There are multiple ways you can have positive charge on an object. I could take, my Newton apple, and suppose it's neutral. It's probably neutral right now. I could give it a positive charge by dumping some positive charge onto it, right? Rubbing it with something that wants to kind of take particles and put it on here that has some sort of positive charge. Another way to do it is I could take an object and maybe rub the apple, and maybe some electrons from the apple leave the apple, leaving it overall with more protons than electrons, so it would have an overall net positive charge. That's another way to do it. You know, just by saying that the object has a positive charge really doesn't tell you kind of which of those answers is correct. Now, more often than not, it is the case that it's the electrons that typically are moving around. And so when you rub, like when we rubbed the balloon with my hair, really what happened is that electrons in my hair kind of more easily wanted to travel over and would rather have hung out on the balloon. And so the electrons moved over to the balloon, giving it an overall net negative charge. When you rubbed the pipe with the fur, same idea. The pipe liked having electrons, the kind of atomic structure that made up that pipe more readily could take on additional electrons in their orbits, and so the electrons kind of wander over to the pipe. Versus the glass, where you rub the glass with silk or something else, and the electrons would much rather be off the glass and go over to the silk, and so then it was left with an overall positive charge. So in this case, how many fundamental charge units are in excess on the object? Well, in that case, then I know that it's some multiple of E. So if I wanted to really write this out explicitly, I know that this charge Q is going to equal some number N times the fundamental charge unit E. I'll even put the plus because it's a positive amount, or it's plus E. So then the number is then just Q divided by E, which when you work it all out is something like 142. Right, so there's perhaps 142 electrons left, or maybe 142 kind of particles or protons moved onto the object. But again, it's usually the electrons that are moving around. So similarly, just a word that might cause some confusion but shouldn't, right? You might hear the phrase like charges canceling each other, like a neutral object, right, where there's the same amount of positive charge and negative charge and they cancel one another. Again, what they mean is that a neutral object has an equal amount of both. It's not really that they're finding each other and disappearing, though that can happen in high energy particle physics. But really what they mean by canceling or charge canceling is that they're in equal amounts, so that the net is zero. Right. One more comment on the numbers. As you might notice, the fundamental charge unit, 10 to the negative 19 coulombs. Very, very small. An actual coulomb is actually an extreme amount of charge. To give you an example, a lightning bolt usually transfers about 10 to hundreds of coulombs of charge in a single lightning bolt strike, which is actually a good amount of charge. And we'll learn that the fact that the lightning bolt actually does that very quickly is what makes lightning bolts dangerous. But the common electrostatic charges that we typically deal with kind of range from pico to nano to maybe even up to milli. So, of course, we might want to use prefixes. So it's good to review some prefixes. So a pico coulomb, or usually just called like PC. A pico coulomb is 10 to the negative 12 coulombs. A nano coulomb, or just NC. Nano, good things to remember. Nano is billionth, and order of magnitude, billion is 10 to the 9, so billionth is 10 to the negative 9. Micro coulombs, typically we use the Greek letter mu, because M is already used for milli, so micro coulombs. Micro is the same as a millionth, and I got, again, good order of magnitude to memorize. Million is 10 to the 6, so millionth is 10 to the negative 6. And then millicoulombs, or MC. Milli is thousandth, 1,000 is 10 to the 3, so it's thousandth, 10 to the negative 3 coulombs. If you want to use, it's always nice, because prefixes can then usually make the scientific notation numbers a little bit simpler. All right, what other properties do we have? I think we're ready to move on. What other properties do we know about charge? Actually, I think there's only one more I really want to talk about. We also know that charge seems to possess a conservation law, that for closed systems, charge is conserved. So for closed systems, there's a law of conservation of charge, or we can say that charge is conserved. And there's some words here from first semester physics that we should remind ourselves of. So a closed system, well, actually let's first start with system. What do I mean by system? That is the object or objects under study. You likely saw this in the context of when you were, say, doing Newton's laws in Physics 1. Right? If I wanted to, say I have this book and I have this apple. If I wanted to study, say, the forces on the apple and describe the motion of the apple, right, my system would then be the apple. And then by the rules of how you do Newton's laws, you look at whatever's touching the system. So the book's touching the system, so there's a force from the book on the apple. My hand is not touching the apple, so there is no force from my hand on the apple. That's my system. And then we have gravity acting on the apple. But then if I wanted to, say, study the motion of the book and the apple, then my system could be the entire thing. It can have multiple objects in that case. And then again, you look at to determine the forces on that system, you look at what's touching your system. So in this case, the hand is touching the book, which my system was book plus apple. So there's a force from my hand on my system, for example. And then you include long-range forces like gravity as well. So the object or objects under study. We'll review that more as we get into Coulomb's law. So then a closed system then is a system where nothing is entering or leaving the system. There's a little bit more formality I could give to that definition, but for now we can just think of it as nothing is entering or leaving the system. So if my system is the full apple, right, the system remains always kind of the full apple. There's not pieces of the apple leaving the system or objects coming into the system and hanging out on the apple or something like that. So then what does it mean that charge to be conserved, right? So charge is conserved. Conserved is that the kind of total amount of charge is a constant. That charge is allowed to potentially move around in the system, but the overall amount of charge cannot change. Let's use some simple pictures that we can draw. Suppose I have kind of some sort of metallic ball and a rod. And that's going to be my system. And typically I use kind of a red box, right? That will specify my system. And let's suppose that overall the ball has no net charge, but the rod has an overall positive charge of 2. So we kind of have a metal ball plus a metal rod. And so overall the system has a net charge of, say, 2e, plus 2e. And then, and this will motivate kind of the last thing we'll talk about, suppose I let them touch one another. Now, if I were to take a metal ball and a metal rod and touch them with one another, metal is objects that are metal. Electrons have a very easy time moving around in metals. That's what we call a conductor. I'll write that down in a second. But for now, I'll say that the positive charges, right? If we think of the positive charges as things that can move around, they can go anywhere now in the ball or the rod because they can move freely kind of around metal. So before, when they were just hanging out in the rod, as you might imagine, 2 positive charges don't want to be near one another. They'd rather be as far away from each other as possible because we know that like charges repel. Now if I touch the rod to the ball, the 2 charges still want to be away from one another. So what might happen is that one of the charges might kind of flee to the other side of the ball. Because again, they're just trying to get away from one another. And then if I were to separate the ball and the rod, there's now kind of this one charge hanging out on the ball and this one charge hanging out on the rod. But overall, notice that the overall net charge has not changed. Overall charge is still plus 2e in the system, right? The system was closed, nothing came in and out of the system. As a result, the net charge was conserved. The total amount of charge is a constant. Even though in this particular case, each individual object inside the system, notice the net charge did change on those objects. The ball started neutral, the rod had plus 2e, and after we did this thing, at the end of the day, the ball now has plus e, and the rod has plus e. Still adds up to 2 overall, but each individual object now has an overall, or a charge that is different from what it was at the very beginning. Let's just write that down, actually. So, overall charge is always plus 2e. But this process changed the net charge on each object. Particularly by the two objects touching one another. And then charges were allowed to redistribute themselves across the metal. Because again, we can think of metals as objects where electrons are kind of free to roam around. Or we'll just think really in reality it's really electrons kind of moving around. Though we can think of it as just kind of charges moving around. So this is what's called charging by induction. Which is something you'll kind of play around with, probably in lab as well. And again, really it's just all about a redistribution of charges. It's not that I create a charge, but I just redistribute it. Because you can think of it, if you were to zoom out and think of my entire system as the universe, well then, to the best of our knowledge, by definition, nothing is coming in and out of our universe. So the universe is a closed system. The net charge overall in the universe cannot change. It can go from different objects to different objects. The balloon is floated away, so I can't show you that, but I could move charges from my hair to the balloon, but it's all within the universe. The overall net charge of the universe is fixed. Now, whether the overall universe's net charge is positive or negative or neutral, we think it should be neutral. But that's for a different class. So, let's see, what are the other kind of terms I want to talk about before we move on? This is a more conceptual lecture than problem solving. Well, let's write down what I mean by charge flow. So, let's go back to the glass in the pipe. So that's, when you had kind of the pipe and you rubbed it with fur or silk, what ultimately happened is that, and suppose you just rubbed the fur where's my laser pointer, that you kind of rubbed it just at this end of the pipe, that you just kind of rubbed the fur on the end of the pipe. What ultimately happens is that end of the pipe has a negative charge. You can test this, right? Because you could hold that side up to another pipe and they would repel one another, but then you might not get the same result if you kind of use the other ends of the pipes or something like that. Similarly, when you took the glass and you rubbed it with something, if you were to rub just the edge of it with the silk or the fur or whatnot, glass is rounded. What you would have found is that actually it's the end that you were rubbing possessed some charge. And for those objects, the charge doesn't really go anywhere. You moved it. I forget what the word is called. Tribioelectric charging, I think is what's called. The act of charging something by rubbing two objects. you've moved charge on or off the pipe or the glass to give it an overall net charge. But then once left on its own, or if the pipe or the glass were kind of just dangling on a string, the charge would not really go anywhere else. It would kind of just stay where it was dumped onto the object. Versus if you take metal, maybe it's copper, right? And then I have something that I purposely try to like dump some electrons or something onto the metal. What you would find is that the electrons, I'll use negative for electrons, there were two that got deposited on, that the electrons would move around the metal. In this case, since they're like charges, they try to get as far away from each other as possible. So in that case, the charges could more easily move within the metal versus the pipe or the glass, where you could dump charges or take charges off the object, but then the kind of excess doesn't really go anywhere. The charges themselves, or think of the electrons if you want to think of an object moving around, can't really redistribute themselves on the object. So this is the difference of pipe and glass, or what we would call insulators. So insulators, right, materials where charge cannot move freely. Cannot move freely. Rubber is another example of a good insulator. Plastic, glass. Pure water is a pretty good insulator. Tap water is not, because there's a lot of metals in tap water. But if you have pure water in a lab, it's a pretty good insulator. Air is a pretty good insulator, as long as you don't have too much charge, like a lightning bolt, or you don't have two objects super close to one another. Air is a pretty good insulator. So again, I use this example specifically because there's a big misconception where they think insulators means it can't have any charge. And again, the pipe and the glass are examples of insulators that we did give them some charge. But left on their own, that charge didn't redistribute itself or flow. Versus a conductor, where materials where charge can move freely. So, right, metals, tap water, which has metal in it, are examples of some good conductors. So unsurprisingly, copper wire, that makes up electronics, made up of metal. Electrons, if given a reason to, can move freely through that sort of object. And then there are things like semiconductors and superconductors. Superconductors essentially are conducting materials, where charge can flow, that are essentially frictionless. You can think of it as the frictionless version for electromagnetism. Superconductors, there's no kind of friction that occurs as objects or as charge, namely electrons, try to move. So this also can result in this will be the last topic we talk about, of this thing called induced charge with conductors. Now let's go back to the balloon paper example I did at the very beginning of the lecture. I had a bunch of paper. Actually, let me get my balloon. I have a bunch of paper and then a balloon. And right now I'm more or less, right, if I have the balloon sit on the table or touch the ground, and I'm not wearing shoes, and so rubber is a good insulator, right? So and I'm essentially grounding. What we say is grounding these objects, right? They're in contact with the ground, through me, or if I lay them on the table. But essentially all that means is that it has access to a reservoir of essentially whatever amount of charge you want, right? You can think of the Earth as a big bucket of charge, so that if something comes in contact with the ground, right, it will neutralize itself, just by borrowing some charge from the ground. Or maybe, well, I'll go through the examples in a second. So essentially what both of these things start neutral. But then I rub the balloon, which we've talked about, gives the balloon an overall net charge. But then the paper is still neutral. Paper is still overall neutral, yet it still responds to the balloon. And you might then ask yourself, but I thought you needed positive or negative overall to have some sort of force. And you're saying there's no net charge on the paper, yet it still seems to clearly respond to the balloon. So paper, serving as a decent conductor, here's what's going on. Let's just kind of draw it out in pictures. So I have the balloon, and then I have the piece of paper. So balloon and paper. Ball, balloon, whatever. And then I'm going to give the balloon some overall negative charge. And it's brought close to the paper. Now, like charges repel and opposite charges attract. So if there are, and we know the paper is made up of, has both in it, because we know it comes from protons and electrons. So the electrons in the paper would rather get as far away from the balloon as possible. It doesn't want to be near the balloon, because we know that like charges repel. So if the electrons can move freely, they're going to want to go over to the right of the paper. So then what happens is you have your balloon with negative charge, then you have your piece of paper, and the electrons, if they can go anywhere, are going to all go hang out over here. So I can say that the electrons, in this case, move away from the balloon. Now, what does that mean overall? What's happening now on the left side of the paper? It started with no net charge, right? Same amount of positive and negative. Which is why on the left-hand side of the screen, right, I drew the paper with no pluses or minuses. Charge must be conserved. There's nothing leaving the paper or entering the paper, so there must still be the same net charge, which was 0. And we just use it looks like I drew 6 negative signs, right? So the 6 negative signs that came over to the right, that better mean that there's a net positive charge over here on the left. Overall, still neutral, but now that left side has kind of a dearth of electrons, so it has a net positive charge, but then the right-hand side of the paper, all these electrons start hanging out. That has an overall net negative charge, but overall the paper is still neutral. Nonetheless, those positive charges love the electron, or love the negative charge of the balloon. So this positive charge, actually let's label this, right? So this is kind of a dearth of electrons. So overall positive. But then I'll say, again, paper, overall, net charge, 0. Now what ends up happening I use 6 before, I'll 46 again. And this will motivate kind of how we try to quantify these forces, that overall, this attraction here, so the balloon is being attracted to the left-hand side of the paper, though the balloon is being repulsed by the right-hand side of the paper. Overall, that attraction wins. The stuff that's closer has an overall stronger force than the force that you get from the two parts, the balloon and the part of the paper that are repelling one another. And so overall, the paper flies up to the balloon, for example. And this is also another way of where you can overall give an object a net charge overall. And I think this is actually probably more what people mean by charging by induction. But let's say, for example, I have two metallic balls. And right now, and they're connected to insulating stands. And these are metal. So that means charges can move around the balls easily, but they can't go through the stand into the ground. If I then charge one of these balls, right, so maybe this one has an overall net negative charge, you could ask yourself, what does the charge distribution on the other ball end up looking like? And I bring them close, but they're not touching. So then, the electrons on the other ball are going to want to go away, so they're going to flee to the other side, leaving an overall net positive charge on the left. Because the positive charges, right, if they could move, would want to, ideally they want to hop over to the other ball. But you would get a charge distribution like that. I could then, what if I then, I'm not going to let the balls touch, but I'm now going to connect one of the balls to the ground. Right, so I'm going to have some sort of wire that kind of connects the other ball to the ground. Usually it's this symbol that we use, I drew that terribly. Let me try again. I use kind of three lines that kind of get smaller like that. So we've grounded the object. Just meaning we've connected it so that if charge wants to flow from the ground to the object, or from the object to the ground, it can. We could ask then, what happens to the charge on that ball on the right? Now the positive charges, again, they want to be close to the ball, right? These positive charges, let me use the highlighter, these positive charges are happy right where they are because they are attracted to the negative charge over here. These negative charges, however, want to get as far away from this ball as possible, and now they have a way to do it. Before, they were kind of stuck on the ball. Now these negative charges can get even farther away from these guys. So all of these guys will then move down into the ground. So that overall, at the end of the day, once we disconnect the ball from the ground, this still has all its negative charge on it. But then there will just be an overall net positive charge on the ball because all the negative charges will flow into the ground. There was no reason for the positive charges to go anywhere, so they just hung out. And then when we took away the grounding wire, that ball then gained an overall net charge. So that's another way to charge objects. And again, it's by just a redistribution, right? It's all about redistributing in these particular objects. So in the problem sets, we'll work through kind of quantifying, building some intuition about what a coulomb is. We'll look up, how many coulombs are in a penny, for example, to try to give us a better feel for those numbers. And I think, I think that will probably do it for today. I can make one quick comment about charge conservation, in that we can think of that charge is conserved That is different than saying that charge cannot be created or destroyed. You actually can destroy charge and create charge. And again, this is a high energy particle physics sort of thing. We don't really see this. But you can get this if you have, particle colliders like at CERN, and you start throwing things against one another, or you have very highly energetic particles, hit little bundles of energy that we call photons. And you can create and destroy particles that way, but still maintain a conservation of charge. So here's kind of one example that you may have seen kind of in these kind of particle accelerator bubble chambers. So in this case, you can have cases where you can have kind of a gamma ray, a photon kind of come in, and that's just pure energy. It's neutral. There's no charge associated with it. It's just energy. And it usually has to hit something, something has to happen to that particle, where then that energy of that particle can actually turn into, the energy of the photon can turn into two actual particles. It can turn into an electron and its antiparticle, which is called a positron. So what's an antiparticle? In the current kind of model of particle physics, every particle has an antiparticle to go along with it. So an electron, which has negative charge, is this thing called a positron, which is the same mass, but it has a positive charge. There's a proton, there's an antiproton. And you might have heard of these things called neutrinos. There are antineutrinos, quarks, antiquarks. There are these antiparticle versions of all the particles that we know of. And with their charge flipped. So again, if something that has zero charge turns into something, it turns into an electron and a positron, overall there's no net change in the charge, right? Came in with zero, and then there was a plus E and a negative E for the positron and the electron. Overall, net zero. You can get the same thing in reverse. I can take a proton and an antiproton and throw them at one another, and one has a positive charge, one has a negative charge. When they hit one another, though, they might turn into a photon or energy. In that case, there's no overall charge. But that's still conserving charge, right? Because you get a plus E and a negative E, they add up to zero. But then when we turn into energy, again, that is a net charge of zero. You're conserving charge, though in that case, you are destroying charge and creating charge. Again, that's a high energy particle physics thing that you might find kind of interesting. All right, we will build on this with Coulomb's law next time.